everyone. Thanks for coming to our talk. Today we're going to be talking about an exciting new browser feature called Trusted Types and how it protects against DOM XSS at scale. Before we move on to our content, we'll do some introductions. I'm Jen. I'm a software engineer at Google. I've been there for over 3 years now, and I broadly focus on deploying security mitigations to Google's web ecosystem.
Hi, my name is Aaron. I also work at Google New York with Jen, working on more or less the same stuff. And unfortunately, unlike Jen, I am lame and boring, so I used a LinkedIn picture instead of one with animals. But fear not, I can redeem myself because I too keep an animal at home. And mine looks more like the logo than Jen's, so no. Cool. But previous to my work in security, I also had a couple other different roles at Google working on product features for end users on like Google Docs and GCP. And before that, I've also worked at Microsoft and several Ruby on Rails shops. And I'd like to point out that Jen and I are both a little bit unique in the security community in the sense that we arrived here from product side. So we approach a lot of these remediations and like security best practices with empathy for the developer. We try to make it as easy as possible for the rest of you so that you can ship the best features to our users while keeping them safe.
All right. Cool. So
as you mentioned earlier, since our team scope encompasses all of Google's web-facing products, and there are a lot of them, you might have used a couple of them, our security protections have to scale for billions of users and hundreds of web apps. And we've seen a lot of different web apps. We've seen ones in different backend stacks. We've seen different front-end stacks. We've seen super bespoke in-house only frameworks. We've seen legacy frameworks that came out when I was an elementary schooler. So we've really seen it all.
Yeah, and here's a brief overview of our talk. So we'll start by kind of motivating our problem and talking about what DOM XSS actually is. Then we'll move on to how Trusted Types offers protection against DOM XSS. And then we'll go over some examples of how to write Trusted Types compatible code from scratch, and then explain how Trusted Types can be rolled out to existing applications with some sample refactorings to follow. So let's start by talking about our main problem, which is cross-site scripting, or XSS for short. So XSS is a common web vulnerability, and the main risk here is when user input gets interpreted as code. It's a type of injection attack, as we call it, where malicious scripts are allowed to run in a user's context. We also call this the kind of remote code execution of the web, as it lets the attacker do anything the victim can. This includes accessing cookies, session tokens, or even manipulating the HTML or the DOM. So it can be very dangerous when it is exploited.
Great. Thanks, Jen. So now that we know very briefly what XSS is, we'll talk about why this is a #1 problem in web security today. So as some of you may know, Google runs what we call a little bit less formally a bug bounty program, a vulnerability reward program in which we reward our security researchers who find and report potential vulnerabilities to us rather than selling it on the open black market, like financially. So as you can see, of the bugs that were reported to us in this data set, a lot of them are web bugs, which makes sense. Google mostly is a web app company. And as you can see, of the web bugs, XSS vulnerabilities are a huge subset. But this is not unique to just Google. Here is a data set from HackerOne, a different bug bounty platform, which encompasses a lot of smaller companies. And their bug bounties show a similar pattern. XSS is a huge part of the reported vulnerabilities. And to drive this point home, there's also data from Mozilla, and Mozilla also shows the same pattern. XSS is a big problem. It's very common. So why is this bug class so prevalent in our industry, and why is it dangerous?
Yeah, it's helpful to mention here that XSS actually comes in many flavors, but today in our presentation, we're focusing on a specific client-side variant of it, which is called DOM XSS. So let's quickly look into what DOM-based XSS is. As I said, it's a client-side variant of cross-site scripting, and it's caused by many DOM APIs just not being secure by default, and interpreting arbitrary strings as code. So in this way, unsafe user-controlled strings are passed to dangerous DOM APIs and converted into code really easily. An example of this is inner HTML. If you pass in a script tag, you have JavaScript execution. So here's a very kind of simple example of how DOM XSS could happen. In this snippet, we take the location hash, which is a user-controlled string. and then assign it to inner HTML. When we assign it to inner HTML, the location hash that you're seeing on the screen, which is like a sample XSS payload, will execute the onError function and we'll see an alert. So now this example kind of seems very obvious, but it is a lot harder in real life because the two lines of code may be separated by a lot more code. They could be in different functions, different libraries, and the data flow can just generally be very unclear. This is an example kind of security engineers use as a proof of concept, but no one codes applications like this anymore, thanks to front-end frameworks like React that abstract away DOM manipulations as a whole, right?
Except not. Modern web frameworks are very structured, but the platform itself still allows these calls. Or in other words, just because the frameworks can abstract away these calls doesn't mean that it prevents users from actually using them. So in this outrage X post, I guess that's what we're supposed to call them now, there is this enterprising developer who managed to sneak in a call to an inner HTML assignment inside a React component. Though the whole point of React is to make sure that the rendering is taken care of by the framework. But sometimes you really gotta reach deep and go for it, I guess. But lines of code like this are very easy to introduce to your code base, but very hard to spot afterwards. And it really just takes one developer having a slightly off day to maybe write this, and it gets overlooked in code review, and then now it's in your production code, and and we don't know it's there until a vulnerability happens. So, and this is not just a problem with inner HTML. There are over 60 of these different APIs that can turn any strings to code that's running on the page. And that's because the web platform was built to be dynamic as a core design principle. We really want to be able to change the code that's running on the page on the fly so that we can ship the most rich and dynamic user experiences to our customers. And as our front-end and client-side code grows more and more complex, not only in the number of engineers that work on the project, but nowadays in modern JavaScript development, we just reach to NPM for any cool package that we can find to add functionality. So there's not only the number of engineers working on the project, but the number of dependencies, any of which can introduce these code patterns. So in summary, there are three main reasons why DOM XSS is still very problematic. The DOM APIs are not secure by default. Client-side JavaScript is dynamic and complex as a design principle. And we also have this added organizational complexity from the number of developers and the number of dependencies. So XSS, or cross-site scripting, is still an unsolved problem in the industry. So do we stand a chance?
And we think we do. That's why we're here. This is where trusted types comes in. So let's talk about how exactly this security mitigation works and why it's been so successful in mitigating DOM XSS. The main idea behind trusted types is to make security decisions explicit and auditable. This means that when we use DOM APIs, we want it to be intentional. The web API is verbose because we want to make it hard to use dangerous DOM APIs by mistake. And when you want to use them, the runtime really wants to make sure that you want to use them. So in this way, attackers can exploit these vulnerabilities in unintended ways, causing DOM XSS. To do this, trusted types will require typed objects instead of plain strings to be passed into the over 60 dangerous DOM APIs that Aaron just mentioned. So in this case, instead of using strings that represent script URLs, that represents an HTML or a script itself, we'll use the typed objects trusted script URL, trusted HTML, and trusted script. We'll discuss how to generate these typed objects later in the slides, but this is kind of the main idea behind trusted types. To go into the technical details a little bit more, there's a backend component to this. We enforce trusted types by using the content security policy response header and using the require trusted types for directive. So this is a mitigation that's implemented in the browser, and we need to tell the browser, can you please enable this for us? Currently, this is only supported in Chromium-based browsers, but we're making good progress with other browser vendors as well. And once we send this header, the browser will reject plain string assignments to DOM syncs and require that typed objects that we discussed in the previous slides be used with these APIs. So if we try to execute this code snippet here, which was the DOM XSS payload from the previous section, we'll see the following error message in our Chrome console saying that we need a trusted HTML instead of a string here. And as promised, here we have examples of how we can generate these typed objects that represent trusted HTML, script, or URLs. We do this by using what's called the trusted types policy. A policy, you can think of it as essentially a wrapper that takes a string and returns the trusted type of your choice. The security guarantee of trusted types usually comes from what kind of processing we apply to the string within the policy. In the first snippet here, to create a trusted HTML, we can apply a custom sanitizer to a string to guarantee that it doesn't contain any XSS vectors. And this is the definition of the sanitizing policy. And in the second snippet below, right here, you can see that how we would use the sanitizing policy on the string value foo before passing it into inner HTML to make the code trusted types compatible and to avoid the XSS vector. Here you have the trusted types violation and the fix for it side by side. On the left, you can see the assignment to an inner HTML, and we're assuming the value here is a plain string. On the right, we have an inline trusted types policy like the one we discussed in the previous slide, and we use the policy's create HTML function to generate the trusted HTML and therefore avoiding the violation. But you don't always have to write inline policies yourself. They are quite verbose and they look kind of ugly sometimes. You can also use a library that supports trusted types such as safe values, which will take care of the policy creation for you. So on the right side here, we have an example of escaping the HTML with the utility function that safe values provides, and this will automatically return a trusted HTML, so it will avoid the violation.
Great. So thanks, Jen. So now that we've seen the actual API for using trusted types, can we build a real-world application with it? So we'll talk about two different approaches here. The first is how to build an application from scratch, from the beginning, to be trusted types compatible, which is a little easier. And then later, Jen will circle back and touch on how to do the second, which is to take an existing application and refactor it to be trusted types compatible. So as you mentioned earlier, there are a lot of dangerous DOM manipulation APIs. So wouldn't it be awesome if we didn't have to think about these at all? And that's where the frameworks come in. We really want to recommend that you start with a framework that abstracts away these potential DOM API manipulations for you. And there have been a lot where we and other open source community members have worked hard to make trusted types compatible. But these frameworks, as you pointed out before, do not prevent the developer from using dangerous APIs. So just because these interactions are abstracted away, the developer might still need to reach for them sometimes. Maybe they need to ship something really quickly. Maybe they didn't know that the best practices were not to use them. So how can you fix this problem? And that is where we will actually start the enforcement of trusted types as early in the development cycle as possible. So as Jen mentioned earlier, we send either this header or the meta tag at the top of your HTML to tell the browser, hey, turn on this feature, block the string assignments. And this is great because this is really the shift left ideology for those who are familiar with cybersecurity jargon. But we really want to surface these errors as early in the development process as possible because the best time to fix a potentially dangerous line of code that you've introduced is right when you've introduced it, when the context of why you wrote that line of code is still fresh in your mind, and you don't have to trace any previous thoughts to figure out why the logic works like this. And furthermore, we will add that if you have tests in your code, and you can enable these headers during your tests, then now you have your CI and CD pipelines and your DevOps processes catching these errors. So in addition to frameworks and the runtime enforcement itself, we want to also advertise a couple tools like the safe values library that Jen mentioned earlier. So the power of the safe values library is really two main pieces. So the first is that this embodies a safe by construction principle by leveraging modern TypeScript's typing system. So essentially, it introduces types so that you can keep track of which strings may contain user input and which ones may not. And having the type system plumb this logic throughout helps you keep track of which strings you need to be a bit more wary of when you're assigning them. And the second is that it provides a lot of library functions and wrappers so that you don't have to deal with a slightly cumbersome trusted types platform API yourself. The other tool that we'd like to point out is tsec. It's a static analysis engine built on top of the TypeScript compiler to potentially look for patterns that might violate trusted types. And if you have a CI/CD pipeline or some DevOps workflow, just stick it in there and it'll tell you when someone might have introduced a line that contains a dangerous pattern. So in summary, start with one of our recommended frameworks and enforce the header early so that you can shift left. And having some of these tools will really help smooth out the process.
Yeah, thanks, Aaron, for describing how to write trusted types compatible applications from scratch. But in reality, we know that most of our job is kind of going into existing code bases and refactoring them to be trusted types compatible. This is where most of the difficulty comes in. Before we dive into the technical details, let's talk about our success stories first to motivate all the difficulties that we're going to go through. And our success with using trusted types to protect against DOM XSS can be explained by one statistic, and that is 0 XSS. This is 0 XSS in hundreds of applications with billions of users developed by hundreds of engineers at Google, and 0 XSS in all the applications that we enforce trusted types for. So many of your favorite Google products enforce trusted types. This includes Gemini, Google Photos, Calendar, Docs, and soon Gmail. We've also invested in enforcement by default, so new products built on modern web frameworks will have trusted types enforcement automatically, so kind of embodying the shift-left approach that Aaron just described. And a word of warning before we get started, making an existing web application trusted types compatible is difficult, especially because we follow a comprehensive refactoring approach with our first-party applications. But we still think it's very worth it, especially because of the runtime guarantees that trusted types provides and how it was able to protect against DOM XSS at such a scale. Now we'll talk at a high level about how we approach the refactoring of an existing complex web app to be trusted types compatible at Google, but this overall approach will apply to other web apps as well. It's important to mention here that trusted types actually comes in two modes. So far, we've only talked about what happens when you enforce it, but you can also enable it in report only. So report only will let you collect violation reports on a designated endpoint, but the browser will not block actions that violate trusted types, while enforcing will block such actions, therefore offering the protection. So we can collect and triage reports without causing any feature breakages. With reporting mode, there will be no user observable changes to your website. As we collect violations, we'll refactor blockers to make our front-end code trusted types compliant, and steps 2 and 3 can be repeated until we're confident that we're not shipping any code that includes any trusted types violations. Trusted types reports tend to be noisy. This is also something to keep in mind because we don't control the user-defined browser environment. Oftentimes, there might be extensions or even malware running on a user's setup, so we'll spend some time sifting through the reports to find the actionable ones. Finally, once we're done iterating steps 2 and 3, we can switch to enforcing mode and be sure that our service is protected against DOM XSS. Now let's dive into how we can actually do steps 2 and 3 and investigate some runtime violations. Here we can see, if you open up the Chrome Dev Console, we can see that there are trusted types violations in our console right there. You can also see the stack trace here, which can help. But as we mentioned earlier, there's a reporting mechanism that posts a JSON with some additional metadata of the violation to our backend. We can take a deeper look at what that data is being sent in the network tab of the Chrome DevTools and how this will help with our debugging. So these are the fields that help with finding where the violation actually happens in our code base. Document URI is the first one that comes to mind. This is the actual page or endpoint where the violation happens. This is useful for reproducing what user interaction could have led to the violation. So if it's, I don't know, in your sign-up page, you roughly have an idea of how the violation could be triggered. The second bit of information that's helpful to spot violations is the source file. This will tell you exactly which JavaScript file is responsible for the trusted types violation, and the line and column numbers should help you find the exact call site. One caveat here is that the source file might be empty in certain cases, especially if the violation comes from a script tag that was shipped with your HTML, but that should also give you a clue of where it could come from. We also encounter Chrome extension as a source file for noisy reports, as we mentioned, and those we just think are safe to discard because we're not supporting the Chrome extension. We can also look at the script sample, which carries 2 bits of information. Those are the first one being the sync itself, so which function we used that was violating trusted types. And on the right side, you'll see the value of the string that was assigned to the sync, which should offer some hints as to what it was. So we've drawn up this methodology or like mind map of what an investigation looks like for us once we've actually gotten the report. We'll start with some code analysis, looking at the script sample. The first thing we see is, what is the DOM sync? Are we using inner HTML? Are we using script source, set attribute? So we know what function call to look for when we're looking for this violation. The next is the string value itself. Does it look like user input? Is it code? Is it a hard-coded string? Maybe we could just grep for it easily. And these two combined could help us find the violation in our code base, so we can search for the string if it's static, like I mentioned, or we'll look for uses of the DOM sync that roughly represent what the string value also is. If you still haven't found it yet, and this does happen, we'll do some runtime testing. This is where the document URI could come in handy. So first of all, we can add enforcement header to the page. We can do it in multiple ways. There's a Chrome extension called mod header that can allow you to easily inject headers to any page that you're browsing. Or Chrome, the modern or newer Chrome versions also allow local header overrides, so you don't need anything extra on top of this. Then we'll browse through the page in order to trigger the violation. Hopefully, we can replicate the user behavior here. And then once we've triggered the violation, the JavaScript is likely minified. In this case, we'll look for strings around the violation point. If there's any kind of constant string that wasn't stripped away by minification, this really helps. And then Chrome also allows you to add a debugger specifically for trusted types violations. So you can just keep browsing the page, and once you've hit a violation, it'll stop, and you can investigate the stack trace, the runtime value, which makes things a lot easier. And if you've reached kind of the end of this graph and you still haven't found your violation, and this is less likely, but it does happen, we just tend to infer based on hints. We look at this in context. We kind of investigate all of the open source libraries that we're using. Maybe we're pulling something in from a CDN that we're not actually looking into. After some time, you'll develop some intuition and pattern recognition after just a few weeks of looking at reports.
All right. Thanks, Jen, for taking us through how to debug potential vulnerability reports. So now that we know how to investigate the violations, we can talk about some of the common code refactorings to fix the places that we've now zeroed in. So before we start, I'd like to point out that there are actually two major broad categories of where these violations come from. The first is code that we've written ourselves. It's in our application business logic. It's in our repo. And this one, we will say that is easier to solve because we have access to the repo. We can just send a PR and we'll be on our way. The second category is those that come from dependencies in our code base. And we'd like to point out that important limitation of trusted types is that you can enforce it only if all of the code that's running on the browser's page is also trusted types compatible. And when in modern workflows, when we import things from NPM and then bundle it up and send it to the user's browser, well, the browser engine doesn't know like which pieces I wrote and which pieces just came from NPM, right? So it'll have to block all the dangerous code patterns in the entire bundle. So because of that limitation, we also have to think about what the dependencies might introduce to our code base in terms of these dangerous code patterns. So Jen will circle back and talk a little bit about how to deal with the dependency problem in a bit, but let's dive into, if we wrote the code ourselves, what are some patterns we can use to refactor away the badness? All right, so of the code that we've written, we'll further divide those into two subcategories as well. Places where we need to use the more dangerous or powerful APIs, and places where we really don't. And in addition to that, we also have code that we can't really refactor because we've checked the usage and we can it's either okay by code review, or maybe this is like some pre-existing behavior in a legacy code base, and maybe we need a bit more time to go and untangle it a bit and maybe revisit it later during an exercise to reduce tech debt. And before we move on further, we will make another plug for safe values because the code examples we're about to show you are a lot easier when you have a library taking care of a lot of the operations. So this example is if you have a string that is from the user, but it's probably not going to contain code that should be interpreted as code running on the page, we can just HTML escape it to neutralize some of the bad markup in there. For instance, this will not execute the payload on at the JavaScript URI if we take away the characters, so that it's no longer interpreted as markup. And we like to point out there that escaping is a library function provided by safe values, and it'll not only escape it, but wrap it nicely into a trusted types instance so that the assignments will be considered safe by the browser. But if you're absolutely sure that the string does not contain any markup and can't break the application in any way, we can also just use a different API that doesn't have the power of inner HTML, like text content. And as an aside, this is probably best practices anyway, regardless of trusted types, because this is more performant for the render if you don't kick off another DOM parser-based thing. All right. If we have constant strings in our code, those are probably safe because users can't change the constant strings. And we have library methods and safe values that will turn constant strings into trusted types instances for us. Or if you don't want to pull another dependency, you could also just reach into the web platform API and construct this yourself using a trusted types policy that only is able to return the constant value so that a user can't hijack it and then have it turn their malicious input into trusted types instances. So here we'll talk about this approach called a legacy conversion that we found very helpful in our refactoring journeys. So as we mentioned before, all of the code on a page has to be trusted types compatible for this feature to ship the protections to the users. Now, sometimes when we are refactoring this existing application, we find code that we just really can't untangle at this moment. We think it's probably safe because it's already shipped to production, it's running, and no one's gotten hacked yet, maybe. But we aren't absolutely sure right now, and the type system can't make this call for us either. So for that, we use this thing called a legacy conversion, which is sort of like a giant to-do in your code base. And here we see that we have a library function provided by safe values that we can use to do this legacy conversion. And in modern development tooling, when we have time to address this tech debt, all we need to do is like right-click on VS Code, and it'll actually list out all the usages of this legacy unsafe conversion in your code base. So you can use that as a source of truth on what you have to go back and fix later. All right, and another plug is that if you're playing around with the types that safe values provides, try to do the conversion to a trusted types compatible value as early as possible when the string enters your system. Because we all know that it's no fun to trace JavaScript stack traces, especially if your code is minified, and try to trace where the string comes from and how it entered this call chain. So another counterpart to the legacy conversion is something that we call a reviewed conversion. So a reviewed conversion is a bit more straightforward than the idea of a legacy conversion. It's just a code review, right? Even if the type system can't determine from the hints in the code that it is a safe operation, sometimes a human can look at it and say, like, well, this code obviously can't be exploited because it's doing something quite obvious. And for that, we will use a reviewed conversion to mark it as, hey, this code path is safe. And our API here sort of requires you to actually leave a reason on why we thought it was safe, so that when you revisit this code, we don't lose our train of thought on why we did this review before and why we think it's safe.
Cool. So the fixes Aaron described in the previous section are relatively straightforward when we have full control over the code and we can apply patches really easily. But in practice, we also encounter a lot of violations coming from third-party sources where the path to refactoring may not be as straightforward. So how do we deal with them? The ideal path and the path that we always hope for is that we just patch upstream repositories, we send a pull request, and it's integrated, and then we just upgrade our library. Done. That's a clean integration. There's huge advantages to this. We kind of make the whole JavaScript ecosystem safer, and everyone else who is using the same library can now adopt trusted types without being blocked on this. But unfortunately, this is not always the case. Often our pull requests are just waiting for a long time. We have to have discussions with the maintainers about what trusted types is, how it fits in with the overall repository, and many other cases. Our solution to this so far has been to fork the repository, set up our own private copy, apply our patch, generate the minified JS file ourselves, and hook that into our product to avoid the violation. Now, while this works, you can imagine that it's not really sustainable in the long run. It adds maintenance costs, and if the library is updated, we would need to do additional work to make sure that our patch still works, and it's just something you always have to keep in mind. Another solution to this that we've used and we found successful is a default policy. This is another thing that the Trusted Types API offers. The default keyword is used to define a Trusted Types policy that will be, as the name suggests, applied by default. What this means is if you have a Trusted Types violation and the default policy defined for the specific sync, let's say you have an inner HTML assignment somewhere in one of your dependencies, the browser will automatically apply the default policy instead of throwing the violation. You can use this as a fallback to fix violations without having to update any of your dependencies. And in this code snippet here, we see a default policy defined specifically for trusted HTMLs. And we just apply the DOM purify sanitizer, which is also compatible with trusted types. This way, anytime a trusted HTML violation happens on your site, the browser will call the default policy, which applies sanitization. Another use of the default policy we found really useful is to allow certain static patterns that we can't change in a third-party library. jQuery is one that comes up a lot during our rollouts. A lot of jQuery APIs use inner HTMLs under the hood, especially when creating elements, as you see here. So like a link element or a text area, this is the first thing jQuery does under the hood. Since we can't fix this in jQuery, we can write a default policy to allow only these inputs since we know that they're safe, therefore unblocking our adoption of trusted types. One important caveat here is that since the default policy is applied to all violations of a given type, it might silence some behavior. But the spec offers a nice solution to this. If the default policy returns null, the browser will proceed to throw the trusted types violation, so the behavior is not silenced. In this case, we can check the input for our specific expected static values, which are the link and text area, and still be sure that everything else will throw a violation by returning null after our if statement. The biggest advantage of this default policy approach is the reduction in refactoring of multiple DOM sync call sites. This means the reduced workload on having to manually review and less time spent on figuring out kind of how to refactor each DOM sync assignment in a safer way, as well as avoiding the problems that we had with upstreaming our patches to external dependencies, which was a huge problem. This also happens to be our biggest disadvantage, however. We always say that even though trusted types is only supported by Chromium currently, the rollout process where we comprehensively refactor all violations makes our product safer for all users regardless of their browser, since it promotes safer coding patterns across the code base. When we use the default policy for all violations and go with the kind of blanket sanitize everything approach, the benefit is only for users who use Chromium-based browsers, as it's only applied at runtime. Other downsides of using a blanket policy stem from how hard it is to ensure our sanitizer is working properly. In practice, there's a lot of sanitizer bypasses that happen in the real world, and we probably wouldn't be able to just use the default DOM purify sanitizer, as we might need to add custom attributes and other things. As we mentioned in the previous slide, applying the default policy to everything could also lead to silent behavioral changes not surfaced as violation reports, and this decreases our overall visibility in the process. So there's advantages and disadvantages to this approach. Cool. So we talked about a lot today, so I'll go over some of our key takeaways. We started by introducing the problem at hand and why DOM XSS is a leading problem in the web industry. And then client-side JS is very complex, and DOM XSS vulnerabilities can easily sneak into our code bases, even if we use React, as we saw in our examples. Then we covered how Trusted Types offers comprehensive protection against DOM XSS by enforcing runtime type checking guarantees. And at Google, we've seen zero DOM XSS on applications enforcing trusted types, which was a huge win for us since it comes after a long history of dealing with DOM XSS. And the path to enforcement with a comprehensive refactoring approach promotes safer code patterns across our code base, making everyone happier. We've also touched on a pain point when deploying trusted types, which was third-party dependencies. We can deal with them with a default policy, but we've seen the advantages and disadvantages to that. And lastly, we kind of want to end this with a call to action by saying that please patch and upstream open source libraries that you find during your rollouts. This makes the whole JavaScript ecosystem safer, and the ecosystem will be stronger when we actually all work together. Thank you for your time. This is kind of officially the end of our talk, but Aaron has a demo for you if you guys want to stick around.